fine. Hi, good day. We're Group 1, and we're going to interpret and analyze the given problem set of linear programming. So, it's the linear programming set. So, as you can see, here's our fixed product problem. At first, we must identify the decision variables and objective functions and constraints and fit formula model of the product. So, here's the product.
Alright. As you can see, there is an example of a fertilizer manufacturing company which focuses on two types of fertilizer. Type A, which is high phosphorus, and type B, which is low phosphorus. Below, you can see the table in the problem, which is there's an item as such urea, potash, rock phosphate, and the two types of fertilizer, type A and type B, that tons requires of it. And the last column is the maximum amount available per day and the net profit per ton, which is 15 tons and 10 tons. So in order for us to graph and analyze the problem, the linear programming problem, first we must identify the decision variables in the table, which is the x ton and the y ton. Um, uh, we can see here that there is a um, objective function that focuses on z, variable z, uh, x ton and y ton is equals to the 15x plus 10y, stated in the table, which is the net profit per ton. Okay, so in the decision variable, um, after we have identified the decision variable, we are now focusing on the objective function and its constraints. So we want to find the decision variables a and b that will give us the maximum value of z. Okay, and we do that to subject to the following constraints. So what are these constraints? In the table, you have seen the three items: urea, potash, and rock phosphate. So, pabalik naman sa table. So we can explain it further. Patas. Slide number 2. Yeah. So we have urea, potash, and rock phosphate. In that row, that is the constraints. Okay, so again, we have the decision variables, which is the net profit per ton, and the objective function, which is z, variable z, and the constraints, which is the three items stated in the table. So in order for us to how do I say this, to interpret the constraints, so sorry, urea has requires 2 tons of fertilizer on type A fertilizer and 1 ton of fertilizer on type B, and its maximum amount available per day is 1.5. We can mathematize that in 2x plus y less than or equals to 1.5. So that's it. That's the simple constraint of it. Or how can we find the constraint when there is a table given? So following the potash, 1 ton and 1 ton for type A, 1 ton for type B, x plus y. Since it in math, in linear equation, when there's one, it we can variable it into x variable. Yes, x and y. So x plus y is less than or equal to 1, 2, because that's the maximum amount available per day. And last one is 1x. Since there's 0, we can derive it into x is less than 500, less than or equals to 500. So the explicit constraints on the availability on the limited resources. Next slide, please. So we can move on. Ayan. So yan. There's two kinds of constraint. There's explicit and implicit constraint. So the explicit constraints on The explicit constraint and the availability of limited resources as follows that shows in the table, in the presentation. And lastly, the last constraint, which is the implicit constraints, we can derive it by just x is greater than or equal to 0 and y is greater than and equals to 0. We can say that the implicit constraint is the non-negativity constraints. So, implicit constraints requires the value that the division variable must be greater than 0, then its values of a and b, and they should be positive or equal to 0. And the values of a and b should not be negative, which is why we call it the implicit constraint and non-negativity constraints, which is that the value is not as greater than or equal to 0. Next slide.
Now that we've identified the following constraints and identified the object variable, in order to find the feasible solution in our solution, any point on the x and y plane whose coordinates fulfill all five restrictions must be used. Each constraint may be represented by a half plane. Since it is a linear equation, thus if we wish to satisfy two requirements at the same time, all we need to do is discover the set of points in the x and y plane that are in the half plane of each constraint. If we consider the half plane to be a set of points, it is the intersection of two sets. Exceeding on the principle satisfying n constraints requires taking the intersection of n half planes. In determining that any point inside the shaded region is a feasible solution. Which one will yield the best value for our objective function? Let us arbitrarily try the point x0 and y0. At this point, the value of the objective function z equals 15x plus 10y minus 15x0 plus 10x0 will equals to 0.
Objective is to maximize 15x plus 10y. Let us try the line 15x minus 10y is equals to 5,000. Now, note that our objective function is of the form ax plus by is equals to c. We learned that if we keep sliding this line to the right-hand side, we progressively increase the value of c.
The area on graph which lies on or below the constraint limit line is visible and therefore left unshaded. Once all constraint limit lines have been similarly shaded, the non-shaded portion of the graph will represent the visible region.
Once you have plotted the constraint inequalities on the graph, you need to shade the area of the graph, which is outside the constraint limits, which is not visible. In such cases, it is useful to consider whether a specific combination like 15x plus 10y equals d, where d is greater than 5,000, is above or below the line is possible or not considering that constraint only. If the combination is feasible, you must shade the opposite side of the line and vice versa. The value of c corresponding to this line is the highest possible value for our objective function. The ideal point where this line meets is our feasible set. In our case, you can see that this is the case, 300 and 900, as shown in the graph. The ideal two of our constraints are represented by the intersection of the two lines, 2x plus y less than or equal to 1,500 and x plus y less than or equal to 1,200.
And lastly, we find the optimal solution of open parenthesis 300 and 900 and close parenthesis. A linear programming problem always lies on one of the corner points of the graph and feasible region. That also gives the maximum value of z by knowing the vertex point and vertex corner point, that we know that the value of z, also the optimal solution, is consists of the value for the decision variable and maximum value of the object function. In our example, Our optimal solutions will consist of the value of A and B and the largest value of Z, and you can get the optimal solution from the table that solves the solution of this linear program in all points. That's all, and thank you.